Right now, somewhere beneath the surface of the Pacific Ocean, water is holding more heat than it has at any point since scientists started keeping reliable records. Not since 1982, not since 2015. Since 1997, the year an El Niño so powerful, it rewrote textbooks to read through global weather systems and left economic damage in the tens of billions of dollars behind it. That record just fell. And the way it fell, quietly, steadily, without a single dramatic spike, might actually be more unsettling than if it had happened all at ENSO. Today, we're breaking down exactly what just got measured in the ocean, why 1997 became the benchmark everyone compares against in the first place, and what this new record actually means for the months still ahead of us. Let's start with the number that matters most. In July, ocean surface temperatures across the planet's non-polar waters hit their hottest monthly average ever directly recorded. Just under 21 degrees Celsius, or roughly 69.7 degrees Fahrenheit, according to Europe's own Copernicus CLIM 8 monitoring service. That number alone surpassed the previous record, which was set only 2 years earlier, in 2023. But the real story isn't just that a record fell, it's what's driving it underneath the surface, in a specific patch of ocean scientists have watched for decades because of exactly what it did back in 1997. That patch of ocean is called the Niño 3.4 region, a stretch of the central and eastern tropical Pacific that meteorologists treat almost like a thermometer for the entire planet. When water there warms significantly above average, it signals an El Niño is forming, and it also tends to preview where global temperatures are heading in the following year. Daily sea surface temperatures in that region have been running around 2 degrees Celsius above their adjusted historical average, and that threshold matters enormously because 2 degrees above baseline is exactly the line scientists use to define what's known as a super El Niño, if that heat holds through the season. Here's where 1997 becomes unavoidable in this conversation. That year's El Niño was, for decades, the gold standard for how explosively one of these events could develop. It formed fast, it peaked violently, and it left behind 16% of the world's coral reef systems dead, along with tens of billions of dollars in global economic damage that economists later traced out to trillions, once the ripple effects across agriculture, insurance, and infrastructure were fully counted. For almost 30 years, 1997 was the event every future El Niño got measured against, the ceiling nobody expected to see broken again anytime soon. This year broke that ceiling months ahead of schedule. Climate researchers tracking the ocean's daily temperature anomalies found that no prior year in the modern satellite record has been anywhere near this warm, this early in its development. Not 1997, which was sitting at 1.6 degrees Celsius ABO-E average, at the same point in its own timeline. Not 2015, another major El Niño year, which was sitting at 1.3 degrees at that same comparable stage. This year's event is developing faster than both of them, launching from conditions that started the year cooler, closer to a La Niña pattern, and still overtaking both historical benchmarks by summer. If you're finding this breakdown genuinely useful, go ahead and hit that like button. It helps this kind of climate coverage reach more people who actually want the real numbers instead of vague headlines. So why is this specific El Niño moving so much faster and so much hotter than the TWO events that used to define the upper limit of what was possible? Part of the answer has nothing to do with El Niño at all, and everything to do with the ocean it's forming inside of. According to NASA, the world's oceans have absorbed roughly 90% of all the excess heat trapped by a century of planetary warming. That heat doesn't just sit quietly at the surface, it accumulates, layer after layer, year after year, raising the baseline temperature that every natural cycle, including El Niño, now has to operate on top of. In 1997, El Niño was adding its warm H to an ocean that hadn't absorbed anywhere near this much background heat. In 2026, it's adding that same natural warming on top of a starting point that's already dramatically elevated. Scientists have a specific way of describing what that combination produces, and it isn't subtle. Nearly every seasonal forecasting model currently available to climate researchers is now pointing toward roughly a 90% chance that this El Niño becomes the strongest ever recorded. Going back through the entire historical dataset, scientists have assembled since 1950. Not the strongest since 1997, not the strongest in decades. The strongest one on record, full stop, according to the overwhelming majority of the world's most sophisticated seasonal forecasting systems currently running. The Copernicus Climate Change Service and the Copernicus Marine Service arrived at this same alarming picture through two completely separate methods of measurement, one built around integrating weather model simulations with satellite and ocean-based observations, the other focused more directly on raw ocean measurements and short-term forecasting. Both approaches landed on the same conclusion independently, which is exactly the kind of agreement that makes scientists take a finding seriously rather than treating it as a fluke of one particular measurement system. What makes this even more striking is how it's showing up across the numbers day after day, rather than in one isolated spike that could be written off as an anomaly. Daily global sea surface temperatures have been tying or outright breaking previous records almost every single day since June, with marine heat waves now blanketing an estimated 82% of the entire world's ocean surface. That's not a regional event confined to the tropical Pacific. That's the overwhelming majority of the planet's oceans, running measurably warmer than they should be at the same time. Let's talk about what this actually does once it starts interacting with the atmosphere, because ocean heat on its own doesn't automatically translate into chaos on land. El Niño works by releasing stored ocean heat back into the atmosphere, shifting wind patterns and rainfall distribution across huge portions of the globe in the process. That shift has already been showing up this year in ways that are hard to miss if you've been paying attention to the news. Record-breaking heat domes have been forming with unusual frequency across multiple continents. France set a new national record in June at 44.3 degrees Celsius. The United Kingdom broke its own June temperature record on 3 separate consecutive days. A humid, oppressive heat event pushed the estimated death toll from that stretch into the thousands across the continent. None of that happened in isolation from the ocean story we've been walking through. The same underlying pattern connects the destructive typhoons that have been battering the western Pacific this year, the relentless temperature records piling up across Peru, and even the unusually quiet Atlantic hurricane season, since El Niño tends to increase wind shear over the Atlantic in a way that actively suppresses hurricane formation there while simultaneously fueling more extreme events elsewhere. There's a term climate scientists have started using specifically for events at this scale, and it's worth understanding because you're going to keep hearing it: a super El Niño. Historically, only a small handful of these have ever been recorded. Events like 1982 to 83, 1997 to 98, and 2015 to 16, each one leaving a distinct scientific fingerprint behind. During every single one of those prior super El Niño years, researchers documented the same devastating chain reaction beneath the surface: mass coral bleaching events, followed by cascading, bottom-up ecological damage as populations of phytoplankton collapse once the colder, nutrient-rich water they depend on gets displaced by the warmer surface layers sitting above it. If this kind of grounded climate science coverage is exactly what you come here for, go ahead and subscribe, because we're going to keep tracking this story with real numbers as it develops through the rest of the year. That ecological chain reaction matters far beyond the reefs themselves, because phytoplankton sits at the very base of the ocean's entire food web. When their populations collapse, the effects move upward through fish populations, through the communities and economies that depend on fishing, and eventually into global food security in ways that take years to fully understand. This is precisely why scientists studying the current event aren't just watching a single temperature number climb. They're watching for the early signs of that same cascading pattern beginning to repeat itself, this time against a backdrop of ocean heat that's already elevated well beyond anything the reefs experienced during those previous historic events. Looking ahead, forecasters expect this El Niño to keep strengthening through the rest of the year, with its peak intensity most likely arriving sometime between November and the following January. NOAA has put the odds of this event becoming officially classified as very strong at somewhere around 63%, a level that would place it among the largest El Niño events recorded since 1950. Multiple independent research teams have gone even further, suggesting there's now a genuine, non-trivial chance that when the global temperature record for the following year gets finalized, it ends up surpassing every previous year ever measured, driven by the delayed atmospheric effects of exactly the ocean heat we've been discussing. That delayed effect is actually a well-established pattern researchers have documented across every major El Niño even T of the modern era. The year in which the event itself develops tends to run warm, but it's the following year, once all that released ocean heat has fully worked its way through the global atmosphere, that historically ends up setting the more extreme records. That exact sequence played out after 1997 into 1998, after 2015 into 2016, and after the more recent 2023 event into 2024. Researchers are now watching closely to see whether that same delayed pattern repeats itself again, this time launching from a substantially higher starting point than any of those 3 previous comparisons ever had. So where does that actually leave us? The ocean has broken a heat record that stood since 1997, not through one dramatic single-day spike, but through months of sustained, stubborn warmth that kept setting new daily and monthly marks almost without pause. The E mechanism behind it combines a naturally occurring El Niño with a background ocean that's already absorbed decades of accumulated planetary warming, and that combination is producing a pace of intensification that's outrunning every previous benchmark scientists have used to measure these events for almost 30 years. The consequences are no longer theoretical or confined to future projections. They're already visible in this year's heat domes, in this year's shifting storm patterns, and in ocean temperature readings that keep landing in territory nobody has ever directly measured before. There's also a practical layer to all of this that rarely makes it into the headlines, and it's worth sitting with for a moment. Warmer oceans don't just raise thermometer readings, they change how storms behave once they form over open water. Tropical systems draw their strength directly from ocean heat, and when that heat sits deeper and more widespread than usual, storms have more fuel. Available to intensify quickly, sometimes strengthening from a moderate system into a major one within a single day. Coastal communities that plan around historical storm behavior are now having to reckon with an ocean that no longer matches the baseline those old plans were built on. Fisheries face a similar reckoning. Warmer surface water pushes many commercially. Important fish species toward cooler water, often shifting their range hundreds of miles from where local industries have fished for generations. That disruption doesn't resolve itself once El Niño eventually fades. Ecosystems take years to recover from what happens next depends heavily on how this event behaves over the coming months, and researchers will be watching every new data point closely as it comes in. But the baseline comparison has already shifted permanently. For almost 3 decades, 1997 was the reference point every major El Niño got measured against. That reference point no longer applies, and scientists studying this event say the ocean's own heat content is now writing a new one in real time, month by month, right in front of us.